Welcome back, everyone. This is Calculus 1, Lecture 11. Today we're going to talk about continuity and differentiability. Okay, so these are two really important features of functions and their implications in calculus. Okay, so first off, continuity. A function is continuous if you can draw its graph without ever lifting your pencil from the page, right? So we're just continuing from left to right. If we have to have some sort of interruption in the middle, or if the function is going into two different directions or something like that, right? These are all different examples of discontinuity. But for continuity itself, we have three criteria. Okay, so the first criteria, the first requirement, is that f actually has a limit as x is approaching a. Okay, so a is some value, some x value on our coordinate plane. As we approach a from the left and from the right, we have to be going to the same place in order for that limit to exist. Okay? And in other words, we can write this with our limits using the limit as x approaches a from the left of f of x is equal to limit as x approaches a from the right of f of x. Okay, so this little minus sign means from the left, little plus sign here means from the right. Okay, so that's the first important piece of information. Beyond that, well, f actually has to be defined at this point, x is equal to a, right? So it's not enough for, well, there to just be a limit, because there could just be a hole in the graph here, right? So we also need this function to be defined, this point to be defined. But this is still not enough, right? Because, well, we're going here, and then the point's defined down here, and then we're coming back up here. That's still not continuous. Okay, so these two alone are not sufficient. We need one more condition, and that is that the limit as x approaches a of f of x is actually equal to where that point is defined. Okay, so where it's defined has to be exactly where those limits are going to from either side. Okay, so where the function is actually going at x equals a should be the same as where it's actually defined, and the three of these together give you a continuous function. Okay, so that's continuity. Then we've got differentiability. So differentiability is what we've been talking about this whole time with taking derivatives, rules of differentiation. A function is going to be differentiable at x is equal to a if its derivative exists at that point, okay? In other words, if our limit definition of the derivative that we've seen before exists, okay? So we've talked about two different definitions of this, the limit as x approaches a of f of x minus f of a over x minus a, or you can think of it in terms of h, which is that little difference between one point and another, and that difference is going to 0. So limit as h approaches 0 of f of a plus h minus f of a, all of it over h. Either one of these will give you f prime of a, which is the derivative of f at a. Okay, so as long as that exists, we have differentiability. Now let's talk about some properties involving the two of these. So if your function is differentiable at x equals a, then it's also going to be continuous at that same point. If it's not continuous, then it can't be differentiable, right? Because if it's not continuous, well, we may not have a point defined here, right? Or our limit may not be going to the same place from both sides, right? We may have some discontinuity of some sort, an infinite discontinuity, a jump discontinuity, however it is, right? So without continuity, we're not going to have differentiability. This is the precursor, it's the prerequisite, it's the necessity in order to establish differentiability. Okay? But continuity enough, or continuity alone is not enough, I should say, to establish differentiability, right? A function can be continuous at a point, but then not be differentiable. It could connect, we can draw it nicely without ever lifting our pencil from the page, but then we still can't take a derivative at it. And this is going to happen in a couple of special cases. Okay. So here are three kind of recurring cases that we keep coming across. The first one's called a corner. So this kind of thing shows up in an absolute value function or something like this, right? So you've got one sort of function here from the left side, you've got another function from the right side, and they meet, but this creates a corner because your slopes are approaching, or they are different from both sides at this point, right? So there's not a singular tangent line that we can draw here. We can draw infinitely many tangent lines through this point, and therefore the derivative is not defined at that point. Okay. The same thing is true at what's called a cusp. So if you have some sort of curve here, and then again, it's dramatically changing direction at this point and going elsewhere, even though it's continuous, how are we going to draw a singular tangent line through this point? We can have infinitely many possibilities, and we have unequal slopes in both of these cases. Okay, and then the last major sort of recurring case is any sort of function that's going to give you a vertical tangent line somewhere in the middle. Okay, so this is a continuous function, and this sort of thing might show up with, say, something like the cube root of x. But at this middle point here, you're going to have a vertical tangent line. And obviously a vertical tangent line has an infinite slope or an undefined slope. Okay, so any sort of function like this, we again cannot take the derivative. Okay, so although continuity is a prerequisite for differentiability, it does not guarantee that your function is going to be differentiable. Okay, so we can have continuous functions, but that alone is not enough to guarantee differentiability. Okay, so let's look at some examples. Okay, so our first example here, we're given a graph. And we've got some kind of complicated piecewise functions going all sorts of different directions. Let's see if we can list, first of all, the x values for which f is not continuous. Okay, so anywhere the function's connecting, we're good. The first sort of discontinuity is going to happen here at x is equal to -5. And this is what's known as a jump discontinuity. Okay, the function is jumping from here. We've got y equals 1, and we're jumping all the way down to y equals -2. So of course, it's not continuous here. And yeah, if it's not continuous, we're not going to be able to take the derivative there either. So that's our first point, x is equal to -5. The second discontinuity is occurring here as we approach x equals 0. So from the left, we're going down to -infinity. But from the right, we're going up towards positive infinity. Okay, so this is an asymptote. This is our vertical asymptote, and this is what's known as an infinite discontinuity. Okay, there's no way to reconcile these. Okay, so although the simplest sort of discontinuity is just a point discontinuity, right? We can just define a point there to fix that, to patch that missing piece. It's not really possible to reconcile a jump discontinuity in the same way, right? We can't, unless we shift one of these functions up or the other one down, they're not going to meet, even if we do define some middle point here, right? And then, of course, for an infinite discontinuity, well, your function's going in two different directions near that point, so that's just not going to be able to be fixed. Okay? So we've got a jump discontinuity at x equals -5. We've got an infinite discontinuity at x equals 0. That's part A. For part B, let's now think about where's the function not going to be differentiable. So of course, -5 and 0, because it's discontinuous there. But like we just saw, there's places where your function can be continuous and still not be differentiable. And our first example of this is happening at x is equal to -9, right? We've got our corner there. So it's coming in with this, well, we've got a negative slope here, and we've got a slope of 0 that is a dramatic shift, and it results in this sharp corner, which again, you can have infinitely many tangent lines running through there. So we do not have differentiability here. Our second point that we've just sort of seen is what's called a cusp. Okay, so it's the same sort of idea as a corner, right? There's a dramatic shift in your slope from either side, but now, instead of dealing with lines, you're dealing with some sort of curves, usually that lead to this. Okay, so we've got a cusp at x is equal to 5, and again, there's no differentiability there. We can't draw a single tangent line. Okay, we can draw infinitely many, rather. So x equals -9, that's our corner. X equals -5, it's discontinuous. X equals 0 was also discontinuous. And x equals 5 is our cusp. So these are all areas where we do not have differentiability. All right. Now, what if, so for our second example, let's suppose we have a piecewise function that's defined. All right, so f of x is equal to 3x squared when x is less than or equal to 1. And, okay, so this is a quadratic function. And then here in purple, it's defined as ax plus b, just some linear function, when x is greater than 1. Can we find a and b so that this function is actually going to end up being differentiable at x equals 1? Okay. Now, we know that if in order for it to be differentiable, well, first of all, it better be continuous, right? So let's start there. We need to make sure that this green piece and this purple piece, that they're actually meeting when x is equal to 1, right? They need to be converging at the same place. So we start by establishing continuity. Okay, and we had, if you remember, well, we have 3 sort of conditions. We need to have that limit. The limit from both sides needs to be the same. Your function actually needs to be defined at your point. Or sorry, your point needs to be defined at that value for x is equal to a, right? And the limit needs to be equivalent to that point, that definition. Okay. So let's run through this. So first of all, we check, okay, well, we're not really given a and b here, so we can't evaluate f of x from here, from this purple side. So we'll use the green function, right? That's actually defined. I can plug in 1 in here, and I can see that, well, if I plug in 1 for x, I'm going to get f of 1 is equal to 3 from here. So the function is defined. This doesn't lead us to any sort of 0 in the denominator. It doesn't lead us to some sort of problematic value, okay? Our function's defined. No negative in the square root or anything like that. Now, beyond that, the limit needs to exist. And just like we said, the limit from the left has to equal the limit from the right. Okay, so we're going to evaluate the limit as x approaches 1 from the left, which is going to be with this function, 3x squared. That has to be equal to the limit as x approaches 1 from the right using this function, ax plus b. Okay, so we go ahead, we set those equal to each other. We can drop the left and right from here, if you like, and then we can just actually go ahead and plug in your x value into here and see what you get. Well, we're going to get, again, 3 times 1 squared, which is just 3. If I plug in 1 for x over here, I'm going to get a times 1 plus b, or just a plus b. Okay, so in order for this to work, in order for these limits to meet from the left and the right, 3 has to be equal to a plus b. Whatever a and b are, right? Now, this by itself is not enough information to establish what a and b have to be, but this is our first condition, okay? Now, luckily, in order for it to be differentiable, we have another property, right? Well, of course, the function needs to be continuous at x equals 1, but in order for it to be differentiable at x is equal to 1, well, we have to make sure we can take the derivative there, actually, right? So the limit as x approaches c of f prime of x has to equal f prime of c. The way we're going to test this is, let's see if we try to take the limit from the left, is that going to equal the limit from the right? Okay, so we've got a left function, we've got a right function. We need to make sure those limits of the derivative f prime of x meet as well. Okay, so our left function was 3x squared. When I take the derivative by power rule, this is going to give me 6x. That 2 comes down, it gives me 6. The power becomes a 1, right? We subtract 1 from there. So I've got now the limit as x approaches 1 of 6x. And on the right side, well, I've got this function ax plus b, right? Again, by power rule, the 1 comes down. I'm just left with a. I can subtract 1 from this exponent, and I get x is 0, which is just 1. So I've got a, and then this constant, this b, is just going to disappear. The derivative of a constant is 0, right? So I've got 6x on the left side, a on the right side. If we evaluate these limits, well, I'm going to plug in 1 for x here. 6 times 1. There's no x here to plug in, so the limit as x approaches 1 of a is just a. So this piece of information tells me that, well, a has to equal 6, okay? So from the first part, when we're trying to establish continuity, both pieces of f of x need to meet at x equals 1. For that to happen, 3 has to be equal to a plus b. And now the derivative needs to be the same from both sides at x equals 1, and that means a has to equal 6, okay? So now let's use both facts and put them together to make this work. 3 has to be equal to the sum of a and b. 6 has to be equal to a. Go ahead and substitute in 6 for a in the first equation, and you're going to get negative 3 is equal to b. Okay, so if a is equal to 6 and b is equal to negative 3, then the function is going to be both continuous and differentiable at x equals 1. All right, so we're going and we're doing this kind of deliberately. We're trying to make this work. So we need to make that continuity element work. Okay, we need to establish the function is defined there. The limit from the left is equal to the limit from the right. And of course that, well, where it's defined is equal to what that limit goes to as well. Right, and then beyond that, well, we need to make sure that the limit of f prime of x from the left is equal to the limit of f prime of x from the right. Okay, so we can make use of both f of x and f prime of x in this case to make this work. All right, so this was a quick look at continuity and differentiability of functions. I hope this helped, and if you found this lecture helpful, please give it a like and subscribe to the channel so you don't miss the next one. Thank you for watching.